Let's talk a little bit about radiation and decay energies. Um, if you have radioactive substances, right, they're going to be undergoing alpha decay, right? They're going to be undergoing gamma decays, right? You'll get gamma rays, right? Alpha, remember, alpha particles are two protons, two neutrons, right? A gamma ray is just a photon, right? And then there's also beta energies, but there's a fundamental difference between the energies of these two. Okay, these ones have what we call discrete radiation. Okay, an example of discrete radiation was the spectra that we looked at in class, right? Those spectral lines were discrete. There were particular energies that the photons had, and they didn't have any energy in between. Okay, when we looked at the sunlight, that was a continuous spectrum, right? So the difference between continuous and discrete is particular energies like this, whereas a continuous spectrum is something like that, right? It's got maybe a peak here or something like that, but it has every single wavelength like that, okay? So this would be a continuous. Did I spell continuous right? I just don't know, okay? You can laugh at me if I didn't. But anyway, continuous versus discrete. So these guys would be discrete. So this is, for example, could be a gamma decay or something like that. I'm just making this up. I really don't know, okay? This could be that could be an alpha energy or something like that, and that's the way it works. And you can look up these energies. These decays have particular energies. You can look up what that energy is, right? And there's a big book of energies, and now I'm sure there's like an online database of these energies, and you can say, oh, we're seeing this particular gamma decay or this particular alpha decay. Now, just a little bit about this, right? Back in the 80s, we used two different things to detect these energies. This is probably, I'm just looking at how sharp and crisp these are. This is probably a germanium crystal, a solid state detector. And these things, the more you pay for your detector, the narrower these little pulses are. But even notice that this is a good detector, but there's still some width to that. The other thing you can do is if you and we did this, we took a regular germanium detector and recorded the data, right? And then we cooled it down, right? We put liquid nitrogen on it and did the same thing, right? Well, when you put liquid nitrogen on it, part of the width of these peaks has to do with the thermal energy of the detector, right? That adds a randomness to it because of the motion of those molecules, right? If you cool it down, these peaks get beautiful. They just get razor sharp like that. Okay, so that was one way to do it, right? And this could be a liquid nitrogen cooled germanium detector. The other thing we did was we used a photomultiplier tube and attached that to a sodium iodide crystal. Sodium iodide is kind of cool because if, say, a gamma ray hits that or an alpha particle hits it, it will scintillate. It'll turn that energy into so let's say here's an alpha particle hitting this, right? The sodium iodide crystal will send a little photon into the photomultiplier tube. And the photomultiplier tube is just a cascade of photoelectric effects. And so it'll hit a plate here, right? And it'll send an electron down to this. And 2 electrons are knocked out of this one. And they'll cascade down to this. 2 electrons, 4 electrons. Pretty soon you've got thousands of electrons, right? And then at the end, we just detect that, right? These things, and what you do is you'd stick the crystal right on the tube, and then you'd wrap it with black electrical tape to block out all the light from the room. And even a dark room, even just like the little lights on the instruments would just send the photomultiplier tube into a frenzy, right? You really had to be dark, right? So it could detect these really minute flashes that this crystal would put off. And photomultiplier tubes would, give you kind of wide peaks like that, but it would work the same way. What was kind of cool was that the guy that in our particle accelerator, right, you'd have the same thing. You'd detect the radiation with that, and he actually went into this the circuitry of the analyzer and put like a little switch on there so we could analyze and get the actual numbers off the peaks and stuff like that. This is the same guy that took a soldering iron to the motherboard of his TRS-80 computer and increased the graphic capability of it. Definitely a knowledgeable man. Okay, now I'm gonna change slides here, right? This is the energy that beta rays, the electrons have in a beta decay. Okay, And this is a continuous spectrum, right? It goes from like the electron has hardly any energy to some maximum amount of energy, okay? And the reason for this is that when you give off and this is by the way, why Enrico Fermi hypothesized that neutrinos existed, right? Because this decay, we can look this up and figure out the decay energy from this by just doing what we've been doing, right? It's a a radioactive decay, so we can look at the mass, right, minus mass, multiply by 931.5 as we do in these complicated times, right? And that gives us a particular energy, which, by the way, corresponds to that, right? So as far as we could tell, the energy of the electrons, they should all be exactly this, if only an electron was emitted. But the reality is that the electrons are emitted on this continuous spectrum. There's a most probable energy, right? But there's no guarantee. It sort of seems random like that, right? Okay. And so either one of two things was true. Okay. Either there was a case where energy was not conserved, and we're not talking about a short period of time here. Okay. We can detect this electron a year later, and it still has this energy, right? So we're not talking about Heisenberg uncertainty type of, energy is not conserved. We're talking that energy is just plain not conserved in the long period of time, right? So either conservation of energy is just out the window. It's conserved sometimes, and in this case, it's not conserved, right? Okay, we don't tend to believe that, right? Or there was a little neutral particle carrying away that energy, right? And of course, that's neutrino just means in Italian little neutral object, right? Nobody doubted the existence of neutrinos. These things don't interact strongly with matter, and so they're very hard to detect. But anyway, obviously we've confirmed that they exist. They actually, I think there's a thing I was reading about where they make them in Switzerland, right? And these neutrinos go through the mountains, and they're detecting them, a stream of neutrinos in Italy. And what's kind of cool is did I say Sweden? Switzerland. I do that. They make them in Switzerland, right? And they send them through the Alps, and in Italy they're detecting them. Neutrinos actually oscillate. So I think they oscillate between the different types of neutrinos, right? And this isn't something that we're going to deal with the IB, but there it is, right? So that's the idea, right? Is that this beta decay is this continuous spectrum, should be discrete, we think, but because the neutrino carries away some of the energy, the electron has whatever's left. Okay. Now, if you add up the energy of this, right, that total energy is this. Okay.